Hi, everybody. Dr. L here with a quick note regarding some questions on the elasticity of demand concept. So just a few things. We saw already that we can think about calculating the elasticity of demand a couple ways. First and foremost was if we were given two different price quantity situations, which corresponds to two different points in the demand curve, then the approach we could take if we calculate the percentage change in price and the percentage change in quantity would just be to plug them directly into the formula where we have the percentage change in the quantity demanded up top of the numerator and the percentage change in price in the denominator. For example, in this particular situation, we are dealing with a case where the price goes up by 10%. So that's a positive increase in the price. But quantity, we know, is inversely related along the demand curve. So there's going to be a fall in the quantity demanded, in this case, by 15%. And we can plug those percentages up in the numerator. I'm going to plug in a negative 15% for Q. Since Q was reduced, I'll plug in a positive 10% for the percent change in P. And this particular situation implies a price elasticity of demand of minus 1.5, which is considered more elastic. Anytime the magnitude or the absolute value of that number, the elasticity, is larger than 1, we say we have an elastic response, meaning we changed the price a little bit in percentage terms, but we had a lot more responsiveness from our consumer segment. The quantity in percentage terms responded by a greater percentage. One problem that we'll run into in taking this particular approach is really a function of the way we calculate percentage changes. So you'll notice in this particular example, we're again moving between 2 points A and B. The standard method for computing percentage changes, typically we look at the change in the numerator, so the end value minus the start value, and we divide that by some reference point. A lot of times the reference point you will use is the starting value, but we could think about computing percentages with respect to the reference point being the ending value as well. And the choice of reference point is somewhat arbitrary, but let me just show you the problem. If we were moving from A to B, then calculating the percentage change in the price means the ending price would be 250. The initial price is 200, and as a fraction of 200, it looks like the price goes up by 25%, right? There's a $50 increase on a $200 price, which is a 25% increase on the old price. Okay, but the problem that we're going to see here is if we were to move in the other direction from B to A, okay, then the reference value, the start value would change. Okay, so just to see that here, if we use the standard method, the elasticity can change depending on what your starting point is. So we just saw from A to B, P goes up by 25%, Q falls by 33%. So the elasticity would be negative 1.33 when we move from A to B. However, if we move from B to A, meaning the original price was up at 250, now when we drop the price by $50, that only represents a 20% fall in the price. And the change in quantity from 8 to 12 represents a 50% increase in the quantity, giving us an implied elasticity of negative 2.5. Now note in both cases, we're still able to identify that that price change implies we have an elastic demand, since in both cases, the absolute value is bigger than 1 in magnitude, right? 1.33 and 2.5. But this inconsistency presents a little bit of a problem just because we move from A to B instead of B to A. Shouldn't imply differences in price sensitivity necessarily. So one way the textbook suggests fixing this is to actually calculate the percentages by using the midpoint right between A and B, right in the middle of the demand curve between A and B as your point of reference. And we're going to use that regardless if we start at A or if we start at B. That way, when we calculate percent changes, the percent changes will always use the same reference point. So the elasticity value will not be different moving from A to B relative to from B to A. So using that midpoint method here, we're going to basically compute the percentage change by making a small adjustment. We're going to take the end value minus the start value, and we're going to divide it by the midpoint. And the midpoint is just the linear average, smack in the middle between those two values. And again, if you're applying this approach with respect to both the quantity and the price, it's not going to matter which value you're using as the starting point and which is the ending point, because we're using the midpoint as the point of reference in either case. Again, keep in mind, if we're dealing with demand curves, elasticity should technically be negative. Sometimes the book will only report a positive value, but they'll tell you it's a demand elasticity. And we know the law of demand holds, and that implies there's a negative or inverse relationship between P and Q. So again, those values for a demand curve should generally be negative if that demand curve is sloping downwards. Okay, so here's a real quick example. If we use the midpoint method on the same exact problem, now when we move from a price of 250 to a price of 200, doesn't matter where we started and where we ended, the midpoint between 250 and 200 is 225. So now when we calculate the percent change in P, regardless of where we start, I'm going to get a 22.2% change in the price. We can apply the same idea to the percentage change in the quantity. So the midpoint between 12 and 8 is exactly 10, which implies a percentage change in Q equal to 40. Now, when we calculate the elasticity of demand using the midpoint approach, we get a magnitude value of 1.8. Again, this is the absolute value, but we know the sign of that thing should be negative because demand curves slope downwards. Okay, we will also discuss the idea of calculating the elasticity at a particular point on the demand curve. I didn't have a chance to cover this explicitly in class, but there is a way you can think about taking those 2 points, A and B, moving them really, really, really close together. So in the limit, they're very small. There's a very small difference between the prices and quantities, and we can actually think about calculating the elasticity at a single point as opposed to computing the elasticity that's implied between two different points, between two different price changes or two price quantity situations. So I'm going to show you just a little bit of algebra of how to actually do this computation. And I'm going to start with our definition of elasticity of demand, which is the ratio of the percentage change in the quantity demanded with respect to the percentage change in the price. And what we're going to do next is we're going to substitute in for the percentage changes. So percentage change in Q is just the change in Q divided by the reference value. And again, it doesn't really matter if you're using the beginning point, the end point, or the midpoint here, because we're moving those 2 points really close together as if we're calculating the elasticity at a particular price quantity situation. What I'm going to do next is I'm going to take the fraction in the bottom, the delta P over P. I'm going to flip it upside down and I'm going to bring it up top. So it is now reciprocated. Okay, and then we're going to do a little bit more algebra to get this in a place that will elicit some, I think, familiar concepts. So the next thing I'm going to do is I'm going to take all the terms with deltas and I'm going to associate them together. Okay, and this is a legal maneuver since everything is multiplied or divided. So I'm going to move the delta P underneath the delta Q, and I'm going to move the Q underneath the P, the quantity demanded underneath the price. And the very next step, which is really the last step here, aside from a little bit of interpretation, is I'm going to now take that first term in parentheses, which involves the deltas, and I'm going to bring it back underneath the second term. So remember when we brought the fraction underneath up top in that second step, we had to flip it upside down. When we bring the fraction back underneath, we also have to do the same thing, which means that delta QD over delta P, when I bring that underneath, becomes delta P over delta QD. Now, if you were given the price that you were interested in, we could plug that into the demand curve equation. We could figure out the quantity, which means I know P, and I would know Q, and I could plug those into the top of the expression that we had just derived. The bottom of the expression takes a little bit of graphical interpretation, but I think once you see it, it should become fairly clear that the bottom expression, delta P divided by delta Q, that is just the slope of the demand curve if we thought about comparing two different points, right? Any very, very small price change, right? Delta P is the rise of the demand curve. Delta Q along the quantity axis is the run of the demand curve. So the denominator here is actually the slope of the demand curve. And I would like to just wrap this quick segment up here by going through a numerical example so you can see how to apply this idea and compute the elasticity of demand at a particular price or at one single point on the demand curve. So here we go. Okay, we're going to be given the equation of the demand curve, and we talked about the difference between the inverse demand curve equation, which is in P equals form, versus the direct demand curve equation, which is in Q equals form. But the inverse demand curve equation tends to be a little bit more convenient because P is on the vertical axis. So we actually have this written in Y equals B plus MX form, right? Where P is the Y variable, Q is the X variable. And the question we want to be able to answer here is we want to be able to compute the elasticity of demand at the point where the price is equal to $25. Okay, we're going to basically take a three-step approach here. We already know the price. So the first thing we're going to do is we're going to plug the price back into the demand curve equation for P, and we're going to solve for the quantity. So if we do that, we find a quantity here of 37.5 units. The next thing we have to do to apply our formula is we have to identify the slope of the demand curve. And I mentioned, because the demand curve is already written in the inverse form, P is the Y variable, Q is the X variable. So all we have to do is look at the coefficient on Q, which is -2, which must be the slope of that demand curve. So we have our slope. We know the value of P is 25. We know the value of Q is 37.5. So now we can apply the formula here, plug in those values, and we see that the elasticity of demand at this particular point on the demand curve, where P is 25, where Q is 37.5, is exactly 1/3. Okay, so this video, all we did was we compared the difference between calculating the implied elasticity of demand across 2 points on the demand curve versus computing the elasticity of demand instantaneously at a single point on the demand curve. Hope that was informative. I will see you all shortly. Have a good one.